This follows directly onto the other two parts. We're going to simplify Boolean algebraic expressions and then verify that our simplifications are correct by using truth tables. There are three types of rules that we use to simplify Boolean expressions. These are the postulates, the algebraic properties, and the theorems. All of these are given on the formula sheet. So our job is just to recognize which one we need in order to perform the simplifications. And you'll just indicate as you simplify which of the rules you're using. We'll go through each one just to understand them a little bit better. But again, big picture, we're just interested in applying them at this point. The postulates are the most intuitive ones. These are the ones that we looked at with our truth tables. So if we have an input A, we know that that can have a value of 1 or 0. That's the only option we've got in the Boolean world: true, false, on, or off. So some are particularly intuitive. If A is equal to 1, it's not equal to 0. And if it's equal to 0, it's not equal to 1. You'll recognize the next three directly from part 1. We looked at the AND gates, in which case the output is 1 only if both inputs are 1, and the OR gate, in which case the output of 1 is 1 if either of the inputs is 1. And then the slightly odd XOR gate, remember the XOR behavior is a little bit different than the OR, because if one or the other but not both, that's when we get an input of 1, when one or the other, not both, is equal to 1. And then finally we have our negations. If something isn't a 1, it's a 0, and vice versa. Double negation just returns the original. So not 0 is once again equal to 0, and the same for not 1. The algebraic properties aren't too much trouble for us either, because we're used to these from regular algebra. Think of this as the commutative property for algebra, like x times y is equal to y times x, or 2 times 3, if you want to substitute in numbers, is equal to 3 times 2. It doesn't matter what order you do the multiplication in. Similarly, the order of inputs into an AND gate is irrelevant. A and B is the same as B or A. B and A. These are the ORs. A or B is equivalent to B or A, and the same is true for X or. The associative property is another familiar one. If I take two numbers, 2 times 3 times 6, and multiply them together, it doesn't matter what order they're in, as long as I choose them at least once, or at most once. So the brackets here are suggesting that we do B and C first, and then take the output there and run it through an AND gate with an input of A. But we could do it in the opposite direction, in that we could start with A and B and then run the output of that into an AND gate with C. These are identical expressions. The inputs, for a given set of inputs, the output would be identical. The same is true for OR, and we can guess that because we know that the same is true for addition, and it works for XOR as well. The distributive property is another familiar one. Do make sure you can go in both directions here. But if you think of A and B or C as a strictly algebraic expression rather than Boolean algebra, we know that we would simplify this by multiplying A and B and then multiplying A and C. Similarly, you'll recognize that both of the terms in the output have an A. So we've got a common factor, the A, that we only have to write once and then multiply by B times C. These also fall into distributive property, but they're a little less intuitive. This looks like we should be able to FOIL it, and we kind of can, but the output isn't what we'd expect. So we are largely going to rely on our formula sheet for these ones. How do we verify that this is correct? We build truth tables. We check that the output from a truth table is the same for the left-hand side of an expression as it is for the right. And we'll verify our simplifications this way as well. And finally, the theorems. These look a little bit different, but they're really not too bad. This just tells us what happens if we have inputs with variables, and some of those are defined essentially. So we have inputs, 0 or 1, and we're running them through AND gates, OR gates, or through an XOR sequence with some input A. That input A could be, of course, a 1 or a 0. We see that the behavior isn't unexpected. We know how AND gates work. If it's not true that both of the inputs are 1, the output is 0. So if we know that one of those outputs, or one of those inputs rather, is a 0, the output must be a 0. Before an OR gate, well, if we have one input of 0, then the output depends entirely on what A is. If A is a 1, the output is a 1. If A is a 0, the output is a 0. We can look at the XOR gate that way as well. So you can talk through 10, 11, and 12 this way, remembering what an OR gate, an AND gate, and an XOR gate does, what their behavior looks like. Here we just add in Rule 12 some of the negations. So for example, if A is combined with not A, the output is 0. Does that make sense? Let's have a quick look at that one. If the input for A is 1, let's say, well then not A must be equal to 0. And if I take A and combine it with, I just wrote B, but of course what I mean is I'm combining that with not A. What am I doing? I'm really taking a 1 and a 0 and asking what happens when I put them into an AND gate. Well, they're not both 1, so the output is 0. So none of these should be surprising to you. And then finally, the negations work very much the same way as we saw with the inputs. Here we just have variables. Not A is simply equal to A. And if we have A with 3 bars, so not A, that's just equal to not A. Essentially, anytime you have 2 bars, they cancel each other out. Quick look at De Morgan's theorem. How do we get from one to the other? So how do we get from not A and not B to not A or B on the right-hand side? Here's the general progression. We'll take that not A and not B, and we'll write the complement of each variable. So we have not A and not B. These aren't equivalent. These are just the steps to get from the original expression to its equivalent expression. And of course, a double negation cancels it out. So now we have not A and not B. And that follows directly. Those two are equivalent. And we're told to change all the AND operators to ORs. So I'll put in a plus as we change all the AND operators to ORs. So we first applied a not to each variable. We complemented each variable. Then we changed our AND to an OR. And if it had been an OR, we'd now change it to an AND. And now I'm going to negate the entire expression. Again, it's these two that are equivalent. Or we could have started with the OR and using the same steps returned to the AND. Try to work these out for yourself. I'm calling this magic, but it isn't really. It's simply applications of De Morgan's theorem.